So in this video, I'd like to give you a brief reminder about vectors, dot products, and scalar products. Hopefully you've seen some of this before. If you feel unfamiliar with this material, then please do go away and just practice these things a little bit. Just play around with some simple examples and make sure you're comfortable with them because they're going to be popping up all the time. Okay, well, let's just start off. We're thinking about 3D usually, and so what we do is we use vectors to, for example, track particles. So we might talk about a vector r, and so notation here can either have a sort of arrow on the top or it can be bold, and that is going to have three components. It's going to be the x component of the particle, the y component of the particle, and the z component of the particle. Now I talk about particles here, but they can really be anything. They can be forces, angular momentums, all sorts of different things, and so all you really need to think is it is a list of a set of three numbers which tell you where this vector is pointing in space. One special thing to remember is what we call a unit vector. So a unit vector we denote by a hat on the top like this, and this has the special property that if you take the absolute magnitude of this, it's equal to 1. And the absolute magnitude is the length of the vector. So you would need to take the square root of rx squared plus ry squared plus rz squared. Okay, let's move on to scalar products. Okay, this is also known as a dot product. So what exactly does this mean? So you'll see things like this written down, so r dot v, where r and v are both vectors. They're in bold here. Well, in component form, what this means is if we write these out as components, this means we take the product of the rx times the vx components plus the ry times vy plus rz times vz, and we sum all those things together. Now that is a scalar number, which is why this is called a scalar product. Another way to calculate this is the magnitude of r times the magnitude of v times cos theta. And so it's a sort of pictorial representation down the bottom here. You see that theta is the angle between those two. Those two ways of calculating this are exactly equivalent. It just really depends on what the problem at hand is, which way you'll do it. Most often you'll see it being this magnitude of r times magnitude of v times the cos theta. Okay? Some things to note about the scalar product. You may not have heard these words before, but you'll certainly know what they mean. The scalar product is what we call commutative. So this means that a dot b is equal to b dot a. So, standard numbers are commutative. 2 times 3 is equal to 3 times 2. That's something you're quite used to. And for scalar products, this remains true. You'll see that for cross products, this isn't the case. It's also distributive. So this means that a dot, the sum of two other vectors, b plus c, is equal to a dot b plus a dot c. And also, if we differentiate a scalar product, we end up with the derivative of one of the components, so dA by dt, for example, dot b plus a dot dB by dt. So the dA by dt here is a vector, and that's why you can take the scalar product with b, and similarly for the other term. In the end, that thing at the bottom there will also therefore be a scalar. Okay, so now we move on to the cross product. This is also known as the vector product, and the reason for that is that the result is itself a vector. So the way this is written is r cross v, and so in component form it has this complicated expression. What you'll see is that term on the far right there is a vector. In order to work out what those components are, you need to remember the rule for doing this. If you're not familiar with that, I do suggest you go and check your math textbook and make sure you're comfortable with that, as it may be useful in the future. But for now, the main way that we're going to be approaching this is through the cross product of r and v is the magnitude of r times the magnitude of v times sine of the angle between them times a unit vector n hat, which lies perpendicular to the plane containing v and r. Okay, so it lies perpendicular to that plane, but you need a way to work out which direction it's going in. A quick way to do this is what's known as the right-hand rule. What you do is you take your right hand, you take your first finger and point it along the first vector in this expression, which in this case is r. You take your second finger and lie that along and point that along the second vector, so v, and your thumb then tells you which direction n will be pointing in. So if we had reversed these, if it was V cross R, then you'd need to turn your hand over and n would be pointing down this way rather than up in this direction. Why is all of this important? Well, as I said, the cross product gives you a vector, and that vector is perpendicular to R and V, and this is very important because this means that the result of any cross product is another vector perpendicular to either R and V, and moreover, we see that if R and V are themselves perpendicular, i.e. The angle between them is 90 degrees, then we just have R times V times that unit vector. If instead R and V are parallel, then the theta here is 0 and sine of theta is 0, and so we end up with 0. So these are things to remember when you're thinking about the cross product. Okay, so now we can move on to the properties of the cross product. So firstly, unlike the dot product or scalar product, the cross product is anti-commutative. What this means is A cross B is equal to minus B cross A. You kind of saw this a moment ago when I was talking about the right-hand rule and where the n hat lies. If we reverse the the ordering of the two vectors, it turns round that vector. And that's exactly what this minus here is doing. The cross product is distributive, though, in exactly the same way. So A cross B plus C is equal to A cross B plus A cross C in the usual way. And under differentiation, if we take a derivative with respect to time, for example, of A and B, then we end up with dA by dt cross B plus A cross dB by dt. Each of these things in themselves will be vectors, and so your end result is, of course, also a vector. Hopefully these things will be useful, and I think it's worth keeping in mind some of these properties when you're doing some of the physics problems, as they can be very useful in simplifying your solutions.